Here's an infinitely long wire that contains charge along its length. The wire, we'll say, has lambda coulombs of charge per meter. So what that means is if I cut out a 1 meter long segment of this wire, I will have lambda coulombs of charge in total. If I cut out a 2 meter long segment of this wire, I will have 2 times lambda coulombs of charge in total, and so on. The first thing we're going to consider is how do we expect the electric field around this wire to look? Do we expect the electric field to point away from the wire? Do we expect the electric field to point along the length of the wire, or maybe a combination of those two? So let's consider the combination of those two. If the electric field points away and along the length of the wire, that would be implying that the electric field in the vicinity of this wire might look something like this. So here is the electric field if I'm above the wire. Here's the electric field at locations below the wire. At this point in the video, I want you to pause and see if you could come up with an argument as to why or why not this expectation might be reasonable to make. We do not expect the electric field to be directed as drawn in this picture right now. To argue that point, let us imagine that we could stand on the wire. If we were standing on this infinitely long wire and observed the electric field, if we looked in one direction along the wire, we would see the electric field partly directed away from us, and if we looked in the opposite direction, we would see the electric field partly directed towards us. This implies that space itself has a preferred direction, and that is not very natural to expect. Because if we look out in either direction, we see the same thing in the context of the wire and the charge along the wire, we expect the electric field created by that charge to look the same as well. Therefore, we don't want any component of the electric field generated by the wire to point along the length of the wire. However, having an electric field that points away from the wire is okay. That will look the same in both directions. So we can expect that the electric field should be able to be directed away from the wire. Also, we could have an electric field that is directed towards the wire. That would just basically be the exact same thing. Towards the wire could be thought of as negative away from the wire. Let's now think about how we expect the strength of the electric field to depend on distance from the wire. Should the strength of the electric field depend on the distance from the wire? As a first guess, we might say yes, that's a reasonable expectation to make. Also, we do expect when an object is infinitely far away from you, it should not be able to affect you. However, on the other hand, consider this. If we are standing 1 meter away from the wire, or 10 meters, or 100, or 100 million light years away from the wire, and we look at the wire, we see an infinitely long wire in both directions that contains electric charge. So no matter how close or far you are from the wire, you see the exact same picture. So should the strength of the electric field depend on distance from the wire? Maybe, but it's not obvious, and we don't want to make any assumptions. What we're going to do is we are going to apply Gauss's law to this wire. When we work with Gauss's law, we will need to come up with a closed Gaussian surface that surrounds part of this wire. Our closed surface will not be able to encompass the entirety of this wire because the wire is infinitely long and a closed surface will be finite in size. However, if we are creative with the shape and the orientation of our surface, that won't be a problem. We also want our surface to possess a high degree of symmetry with respect to the wire. One way of thinking about symmetry is to imagine you look at an object and you see a certain image, and then if you change your perspective, if you look at that object from a different location, if you see the exact same image, then you could say that object has a degree of symmetry to it. At this point, pause the video and see if you could think of a shape for a surface that will possess a high degree of symmetry when we place it in the vicinity of this wire. The Gaussian surface we're going to use for this exercise is a cylinder. Specifically, we will choose a cylinder whose central axis coincides with the wire itself. So in this picture, I could say here will be the sides of the cylinder, and then here is the left cap of the cylinder, and here is the right cap of the cylinder. Now the wire will pass through the left cap of the cylinder over here, and the right cap of the cylinder over here. We'll also say that this cylinder has a radius r and a total length L. Why did we choose a cylinder as opposed to a different shape? One beneficial aspect of a cylinder is, notice that every point on the side of the cylinder is the same distance from the wire based on how I drew this. A consequence of this is if the electric field depends on the distance from the wire, then the electric field at every location on the side of the cylinder will have the same strength. Overall, this cylinder as a closed surface has three parts. We have a left cap, we have the side, and we have the right cap of the cylinder. So when we apply Gauss's law with this closed surface, we will need to account for the flux through each of these three parts of our closed surface. We're going to now apply Gauss's law. So Gauss's law says the total flux through a closed surface is equal to the total charge inside that surface divided by a fundamental constant of nature. Let us first look at the left-hand side of Gauss's law. The total flux through the cylinder, as I said, is going to be the flux through the side of the cylinder plus the flux through the left cap of the cylinder plus the flux through the right cap of the cylinder. So I could write that as the total flux through the cylinder is going to be the flux through the side plus the flux through the left cap plus the flux through the right cap. Let us first consider the flux through the side of the cylinder. I said that the side of the cylinder is the same distance from the wire no matter where you're standing on the side of the cylinder. So I expect the strength of the electric field to be the same everywhere on the side of the cylinder. The way I am thinking about this problem is I'm imagining that the side of the cylinder is made up of many little patches or tiles. So here is a tile on the side of the cylinder near the top of this picture. Here's another tile on the side of the cylinder. Here's a tile near the bottom of the cylinder. If I look at the tiles on the cylinder, the direction of a line that is perpendicular to the surface of the cylinder will point away from the wire. And the direction of the electric field will point away from the wire as well. So through each of these tiles, no matter where I am on the surface of the cylinder, the flux through that individual tile will be the strength of the electric field at the location of that tile, times the surface area of that tile, times the cosine of 0. The direction of the electric field points away from the wire, and the direction that is perpendicular to the surface of the cylinder points away from the wire as well. They are parallel with each other, that's why I have cosine of 0. If I add up the flux over every tile over the entire side of the cylinder, the electric field will have the same strength over the entire side of the cylinder because the entire side of the cylinder is the same distance away from the wire everywhere. I could then write the total electric flux through the side of the cylinder will be E times the area of the side of the cylinder. So what is the area of the side of the cylinder? I could imagine creating a cylinder by taking a flat piece of paper and rolling it. So if I begin with a flat piece of paper, let's say this paper has a length L, and then I roll the paper up to create a cylinder. I could say that the total height of this piece of paper will be the same as the circumference of the cylinder. So the total height of this paper will be 2 pi r. So I could write the area of the side of the cylinder is going to be L times 2 pi r. So the total flux through the side of the cylinder is going to be E times L times 2 pi r. Now let's think about what we expect the flux through the left cap and the right cap to be on the cylinder. If I were to draw a line that is perpendicular to these surfaces, a line that's perpendicular to the left cap will point along the wire in this direction. A line that is perpendicular to the right cap will point along the wire in this direction. However, remember that we said the electric field at any location always points away from the wire. So at this location, the electric field will point here. At this location, the electric field will point like this. And no matter where you are looking, no matter where you are on the left cap or the right cap, the angle between the direction of the electric field and the direction that's perpendicular to that cap is always going to be 90 degrees. This is a 90-degree angle. This is a 90-degree angle. If I'm above the wire, the electric field will point upward, but still, the direction of this electric field is perpendicular to a line that is perpendicular to the cap. So the flux through a patch, no matter where you are looking on the two caps of the cylinder, will always be 0, because we would have flux in this case is equal to E times A. E is going to be some value that is non-zero. A will be some value that's non-zero. But then we have cosine of 90 degrees. And cosine 90 degrees is equal to 0. So this ultimately is going to be 0. To connect this with the solar panel analogy from the first video on Gauss's law, you could imagine that this is the scenario where the solar panels are completely pointed away from the sun, so all the light passes either above or below the solar panels. So from this, I could say the total flux through the entire cylinder is going to be equal to E times L times 2 pi r. And these two terms are going to be both equal to 0. Let's now consider the total charge enclosed within our Gaussian surface. So we're looking at the right-hand side of Gauss's law. How much charge is enclosed inside our surface? Well, we said at the very beginning, the wire has lambda coulombs of charge per meter. If I have 1 meter of wire, then I will have lambda coulombs of charge. If I have 3 meters of wire, I will have 3 times lambda coulombs of charge. For a cylinder of length L, I could say Q enclosed will be equal to lambda times L, total coulombs of charge. So let's now compare what we have here to Gauss's law and see where that leads us. I could say that the total flux through the entire cylinder, which is E times L times 2 pi r, is equal to lambda times L over epsilon naught. And if I look at this, I have the length of the cylinder on both sides of this equation. The length of the cylinder will just cancel out. And if I bring the 2 pi r to the other side, I end up with the strength of the electric field on the surface of the cylinder is equal to lambda over 2 pi epsilon naught times r. So let's think about what we did here. We found that the strength of the electric field, a certain distance r away from a wire, is given by this equation. This is the exact same equation that was presented in a previous video, but in order to arrive at that, we did not need to compute any integral. We just needed to apply Gauss's law and make a few arguments from symmetry. To finish this discussion, when we placed a cylindrical Gaussian surface around our infinitely long wire, we said that surface has a radius r and a length L. Now this radius and length are completely arbitrary. We went through a few steps in our derivation, we applied Gauss's law, and we ended up with an equation describing the strength of the electric field at every location on the side of the cylinder. However, remember, every location on the side of the cylinder is the same distance away from the wire. When we look at this equation, we should not think of this term r as a radius. We should think of this term r as the distance away from the wire. Again, remember that r and L are completely arbitrary. A Gaussian surface is not a physically real object. A Gaussian surface is just a surface that we invent for mathematical convenience.